We're now going to talk about two models of gravitation. One is the flux model, total gravitational flux model, that you encounter in the problem sets, and the other is Newton's model, as he stated it, more or less as he stated it, which you will also encounter in the problem sets. And we're going to see that the two models are completely equivalent. One model tells us exactly the same thing that the other does, and all the results obtained from one model can be obtained from the other model. There's no difference between the two models, except in our way of looking at things. Now, I start with the gravitational flux model simply because flux is something that occurs when we study electrostatics, when we study magnetism. It's a very important concept in physics. It occurs in other places too, and I want to start you out thinking about flux right now. So we say that if we have a mass m, wherever we are, it doesn't matter where we are, that mass emits sort of a total gravitational flux of 4 pi times big G times m. Where big G, and I haven't verified this, I haven't looked it up, this is the way I remember it, 6.7 times 10 to the negative 11th Newton meter squared per kilogram squared. Might be 6.6, you'd better look it up. Might be 6.64, but that might be another constant. There are a couple of constants around there, and I'm leaving it to you to determine what those are. I could step aside for 10 seconds and open a book and find it, but I don't want to do that. I want you to do that. Okay. Now, just like a light bulb emits a flux of energy in the form of light, photons streaming out, and if it's a point source of light, it emits energy equally in all directions. A gravitational flux can be thought of sort of by analogy with that. Now, as the light spreading out from a source, if this was light spreading out from a source instead of gravitational influence spreading out from a gravitational object, a planet or something, then the light energy would get spread over a smaller and smaller area. The light flux would be spread over smaller and smaller area. It would be spread over greater and greater area, so that there would be less and less flux per unit area. And it's the flux per unit area that tells you how bright the light is at that point. Let's say you're trying to read a newspaper by it. You need a certain light flux per unit area to be able to see the paper well. Okay? Well, when the gravitational flux gets spread out, as we've more or less discussed, the gravitational field gets weaker. Gravitational field, of course, is just measured by the acceleration of gravity at a point. So that we're going to say that the gravitational flux is the average gravitational field multiplied by the area. And to find the average gravitational field, you divide the gravitational flux by the area. Just as to find the level of illumination, you would divide the total wattage of the bulb by the number of square meters over which that wattage is spread. So there's one model, and we're going to see the implications of that model. And then there's another equivalent model that's expressed in terms of the force between two objects. And this model is Newton's original conception, that if you have masses m1 and m2 separated with their centers of mass separated by distance r, then the force between those objects is big G times m1 m2 over r squared, where big G is the same number that I gave you just a minute ago. So in a minute, we're going to take a look at the following situation. We have a mass m1 and a mass m2. Mass m1 is 100 grams. We're going to calculate the flux of the 100-gram mass, and then we're going to calculate the gravitational field due to that flux by determining the area of this sphere and dividing the area into the total flux, which will tell us the gravitational acceleration at this point, where we have a second mass of 70 grams. From that we'll be able to calculate the force on that mass, and then we're going to use Newton's formulation to see if the force that we get by the flux model doesn't give us the same thing as Newton's formulation does.